Okay. First of all, before we jump in and talk about the lab, are there any questions about what's happening this week or what's happening with your AP exams? You guys feel okay about all of that? Let's see. Do we have to turn in the packet in any way? That's a good question, Mr. Jam. I haven't decided that one yet. I mean, it's in your best interest to do as much of the packet as you can. You guys are big boys and girls. I might just trust you to do that. I don't know. Yeah, we'll see. Will the packet be due Wednesday? No, the packet will not be due Wednesday. The packet, if it is due, will be due on the day of your exam, kind of like we've always done it in the past. All right. Okay. So let me go over this lab with you. First of all, let me. Okay, yeah, let me just keep this screen share like it is. Okay, so this lab is actually quite simple. Hold on, I have another question from Ms. Young. What do I think the difference in the test we take at home versus at school will be? Are you talking about the AP exam or the exam I will give you this Friday? The AP exam. Okay, that's a good question. So it's going to be free response only. Oh, I see what you're saying now. Okay, so Ms. Young is basically getting at this scenario. What if we are back in school by the time you guys sit down to take the AP exam? If you are back in school at that point, I'm 90% positive. It's still a little unclear to me, but I'm 90% positive that you will still be taking the modified new 45-minute free response only exam. Like that's what everyone is taking this year. I'm 90% certain. So if that's the case, you'll take it at home, or if we're back in school, I don't think we'll be back in school, but if we are back in school, you'll take it at school, and it'll just be 45 minutes for your response. And again, I'm 90% certain about that, okay? Okay, so to the lab. So this lab is really simple. It's just reacting two different chemicals. One chemical is known as crystal violet. I will be referring to crystal violet as throughout the lab paper as CV plus. Now, obviously, that's not a chemical formula. The actual formula for the crystal violet chemical is really long. It's a big carbon-based organic compound. It's called crystal violet because it's violet in color, and it's a dye. It's used to dye things purple. So crystal violet throughout this lab will be denoted like this. It does have a slight positively charged region on that big old molecule somewhere. So we typically will write it like this, CV+. So wherever you see CV+, just know that's the crystal violet chemical. Crystal violet is obviously violet in color, it's purple, and we're going to be reacting it with sodium hydroxide, NaOH, aqueous sodium hydroxide. Now, hopefully you guys know that sodium hydroxide is an ionic compound, sodium ions, hydroxide ions. And when an ionic compound is aqueous, everyone in here knows that we don't just have sodium hydroxide crystals floating around in the water, do we? No, we have dissociated aqueous sodium ions and hydroxide ions floating around, right? So it is these hydroxide ions that we are worried about. Our sodium hydroxide, Ms. Stark says, I don't see you writing on the screen. Oh, okay, give me 1 second, I can fix this. My bad. Thank you so much for letting me know. Let's see, give me 1 second. Maybe. Okay, can you guys see the writing now? Okay, I'm so sorry. Thank you for alerting me to that problem. Okay, so yay. Okay, so our sodium hydroxide chemical is just supplying us with hydroxide ions. Those hydroxide ions are capable of reacting with crystal violet capable of reacting with crystal violet just like this to form a complex, basically. The hydroxide ion is able to attach to that slight positive region of the crystal violet chemical to make something that we could call crystal violet hydroxide or something. Now, remember, CV here is not a chemical formula. It's just a shorthand for crystal violet, okay? Again, the actual chemical formula for crystal violet is quite large. So the interesting thing is that whenever crystal violet has bound with this hydroxide ion, it becomes colorless. So it was a nice crystal, excuse me, it was a nice violet color, and then it becomes colorless. And this is really helpful for us because we're going to be interested in the kinetics of this reaction. We want to know what is the order of the reaction, how fast does the reaction occur. So I want you guys to think about this. What have we measured in the past? What have we measured in the lab setting in the past that dealt with color? Anyone know? Because as this reaction proceeds, if we were to watch this reaction happen, if this was happening in a little vial or in a beaker, we would see the purple color fading away to a colorless solution. Yeah, so Miss Young is mentioning the red 40 dye lab that we did. That was a Beer's law lab. Do you guys remember Beer's law? Beer's law says this: A equals ABC. Who remembers what capital A is? Someone unmute themselves or type it in the chat. This is Beer's law, capital A. Anyone? No one remembers? Capital A is absorbance, how much light is getting absorbed by a solution. A times B was some constant. A depends on the chemical. B was the path length. How long does the light travel through the solution? And who remembers what C was in this equation? Hopefully you guys remember this because this is like the important part.
Isn't it the length?
No.
Like something like that?
B was the path length.
Oh.
Yeah, so Mr. Roberts says concentration. That's correct. So C is the concentration of our chemical. So think about this. As this reaction proceeds, the concentration of crystal violet is decreasing, isn't it? It's a reactant, it's getting consumed in the reaction. And luckily for us, as crystal violet, as the concentration of crystal violet decreases, our solution becomes colorless. So if we are able then to perform this chemical reaction and measure absorbance data as time goes on, that absorbance data is directly proportional to concentration. And remember what chemical kinetics are all about. Remember how we define the rate of a reaction. It's all based around the concentration of reactants, right? As time goes on, these reactants are decreasing in concentration. We can see the concentration of crystal violet by measuring absorbance as time goes on, because absorbance is directly proportional to concentration. So absorbance is going to be like our stand-in. It's going to, it's because it's directly proportional to concentration. Instead of measuring concentration, we can measure absorbance as a way of measuring concentration, and we'll be able to, if we do that over time, we will be able to determine something about the rate of this reaction. So that's how this lab works. Does that make sense? We use a colorimeter. You guys remember the cute little cuvettes that fit into that machine called a colorimeter, and it is able to track the absorbance as time goes on. All right. Okay. So someone answer this question for me. That colorimeter that we had in the lab, it measures how much light gets absorbed by the solution. Remember, light has different colors based on the wavelength of light. You guys remember this, the electromagnetic spectrum. So would we want to set our colorimeter to measure absorbance at a wavelength close to purple, which is a short wavelength, or will we want to set it to a different wavelength? Who knows? Anybody? Well, we've discussed this in the past. What is true about the light that you see when you look at a substance? Like when we look at crystal violet and we see it's like a purple violet color, is that the light that is getting is that the light that's getting absorbed by the solution? No, that's the light that's getting transmitted or reflected through the solution. So my colorimeter, I can set it to measure different wavelengths or different colors of light to measure the absorbance of that wavelength. I do not want to set my colorimeter to measure the wavelength of purple light because crystal violet does not absorb purple. It absorbs the opposite. It absorbs like green, okay? So I would want to set my colorimeter to that wavelength, all right? So anyway, in this lab, our purpose is to figure out the rate law for this chemical reaction. So you guys can all see, hopefully, right down here. You guys can see right here, hopefully, this is the general form for the rate law of this chemical reaction, where big R, capital R represents rate, K represents the rate constant, and then we have the concentration raised to some power. You guys know that those powers, M and N, are known as the order of the reaction. That is our goal in this lab. We want to know what is the order of the reaction with respect to crystal violet. What is the order of the reaction with respect to hydroxide? So that is the purpose of the lab, all right, is to figure out the rate law. We want, in other words, to fill out those three variables. We want to know what K is, the rate constant. We want to know the order on crystal violet, M, and the order on hydroxide, N, all right? So we are going to be able to get concentration versus time data. We're going to be able to get absorbance data. That absorbance is a stand-in for concentration. It basically is our concentration, okay? They're directly proportional. So we're using absorbance instead of concentration because that's all we can measure. And we're going to get absorbance versus time data. So you guys hopefully remember enough about kinetics to understand that if you have time data and then you have concentration data, where again, we're using absorbance as a stand-in for concentration, and you have all these data points, someone tell me, what are you able to do with that data to figure out what the order of the reaction is? Who remembers? I had several videos about this and you guys hopefully practiced it. Time versus concentration data. What are you able to do with it? No one's gonna answer. All right, Ms. Skolma's saying linear regression. Yeah, that is exactly correct. Very, very good. So yeah, remember that whenever we have time versus concentration data, you have all these data points, you're able to plot them and run linear regressions. And you know that if time and natural log of concentration creates a straight line like this, what order of the reaction would that be if the natural log of concentration versus time creates a straight line? Y equals mx plus b.
Would that be first order?
Yeah, excellent. That's first order. Second order is, of course, 1 over concentration. And then, of course, you guys know that 0th order is where the concentration values versus time already make a straight line. Okay, so yeah, what we're able to do then is with concentration and time data, If the natural log versus time makes a straight line, we know it's first order. If 1 over the concentration versus time makes a straight line, we know it's second order, blah, blah, blah. So that's what we're going to do, basically. We have concentration versus time data. In the lab, how are we getting that? We are tracking the absorbance as time goes on. It's going to decrease, right? Because as crystal violet, once again, as this reaction right here proceeds, the deep purple color disappears. It becomes colorless. So absorbance of that light is going to drop, is going to decrease. So the concentration of crystal violet is decreasing as time goes on, just like we've discussed. So absorbance is our stand-in that we're able to measure. It's going to be our stand-in for concentration of crystal violet. And we're going to be able to do this, run a linear regression, and figure out if it's first, second, or zero order with respect to crystal violet. This is complicated, though, because these equations that we've been doing only work when your reaction has one reactant, right? This A here represents crystal violet. That is what I'm able to measure the concentration of because it has a color. I can measure the absorbance of light in that colored solution, track how that changes as time goes on. Once again, because Beer's law is true, because absorbance is directly proportional to concentration, my absorbance data is like a stand-in value for concentration. And I can get data, time, absorbance, which is really time concentration, time absorbance data, graph it, and I will know the order with respect to crystal violet. It's going to be more complicated, though, getting the order with respect to hydroxide, because hydroxide is colorless. There's nothing I could set my colorimeter to tell me how the hydroxide is changing. This is probably the most complicated part of this lab, and this is where you guys need to listen very carefully. All right, let me get a different screen share up real quick. All right, let me just do this. Nope, sorry. Just need a surface to write on real quick. Please hold. Okay, someone tell me if you can see the, someone tell me if you can see the writing that I'm doing right now. Yes? Can y'all see it? Yes, yay, okay, neat. Okay, thank you. All right. Okay, guys, so please listen up, because this is where you're going to get confused, and this is complicated. But this is important, though, because I have seen a free response question about this very idea. So we know that this is true. The rate of our reaction is equal to the rate constant times the crystal violet concentration raised to the m times the hydroxide concentration raised to the n. Let me make sure that's the same way I wrote it in the lab report real quick. Okay, excellent. So we're only, through getting time and absorbance data, we are only going to be able to figure out this m value. We're only going to be able to figure out the order with respect to crystal violet. What we want to do is figure out the order with respect to hydroxide as well. We want to get this n value, okay? So what we're going to have to do is run two different trials. We're going to run one trial with a certain concentration of hydroxide, and then run a second trial with another concentration of hydroxide. And you guys should remember this. I'm going to make the concentration of hydroxide tens of thousands of times larger than the concentration of crystal violet. The concentration of crystal violet that I start with is, if I'm remembering correctly, something like 2.5 times 10 to the negative fourth molar, something like that. That's the initial concentration of crystal violet that we're using. But our concentrations of hydroxide that we're going to be using are something like 0.10 molar. And then we're going to do another trial with 0.20 molar. So you can see that these are like tens of thousands of times bigger than this, right? So do you guys remember what happens to this rate law? What happens to the rate of a reaction when one reactant is much, 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 much more highly concentrated than the other. Do you all remember? Well, think about this. As time goes on, what's going to be happening to the concentration of hydroxide? It's barely going to be changing. It's so much larger than the concentration of crystal violet that it's barely going to change at all. In other words, throughout the entire course of the reaction, my crystal violet, I hardly have any of it there, right? It's present in such a small quantity. The concentration is so low that as time goes on, it's basically going to drop to zero. It's going to get completely consumed as a reactant in the reaction. But my hydroxide, it may go to like 0.09998 or something like that. Like it may barely change at all. Does that make sense? Because it's present in such higher concentration. In other words, then this N, I'm artificially forcing it to behave as if my reaction is 0th order with respect to hydroxide, because the rate is not going to depend on the concentration of hydroxide, because the concentration of hydroxide is barely changing. I'm forcing the system to behave that way. Does that make sense? So here's the idea. By plotting time and concentration data and running linear regressions, we're going to be able to get that integrated rate law and know if it's first, second, or 0th order with respect to my crystal violet. I'm going to get to know what M is. To know what N is, the order on hydroxide, I'm going to have to collapse this down into what is known as a pseudo rate law, where the word pseudo means fake. So in trial 1, we're going to have our hydroxide concentration equal to 0.20 molar. This is all in the lab handout. And that is tens of thousands of times bigger than the crystal violet concentration. So that is barely going to change at all. So I can rewrite the rate law like this. I can replace K with K prime, where that's like a new K value. And I'm going to give it a subscript 1 because this is trial 1. If you guys read the lab handout, this may make more sense. Times CV plus to the power of N. In other words, because my hydroxide concentration is so much bigger than the crystal violet concentration, I basically am saying, I'm basically forcing the system to act like N is 0. It's 0th order with respect to hydroxide. The rate does not depend on hydroxide concentration because hydroxide concentration is hardly changing at all. And so I collapse it down into this pseudo rate law. It behaves like I have forced it to pretend like this is the rate law with only one reactant. Does that make sense? So this K prime then, K1 prime, is going to be the slope of the integrated form. So remember, we're collecting time and absorbance data, where absorbance is really concentration data, blah, 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 for this trial, where this is the initial concentration of hydroxide that we're using. And we're going to run linear regressions, see if it's first order, second order, 0th order. And from that linear regression, you're going to get a slope, right? Remember that slope is your K value. And so I'm going to be able to figure out in one trial what the M is. What is the order on crystal violet? Is it natural log versus time? Is that a straight line? Then it'd be first order. Is it 1 over concentration versus time? Does that make a straight line? It'd be second order, blah, blah, blah. I'm going to be able to know what M is, and I'm going to get K. But my K is going to be like a fake K, a K prime, where that has contained in it me collapsing down the hydroxide concentration. So here you can see my K prime is taking the place of K, and OH minus, right? So I've taken those out of the equation, replaced them with this false fake K value, because again, I'm pretending like the hydroxide concentration does not really change, because it really doesn't. So I'm going to get that slope, and it's going to be equal to this. Once again, because that's true, because I've replaced K and OH minus to the nth power with this K prime value. So K prime is this, okay? And then what I can do is do a second trial with a second concentration of hydroxide. This time, I think in trial 2, it's 0.1 molar. And I'm going to do the exact same thing. I'm going to get time concentration data. This time, I'm already going to know what the order of the reaction is. I already found that in trial 1. I know what M is. So I'm going to jump straight to graphing that. And now I'm going to get a new K prime value. And that new K prime value, what I'm calling K2 prime, is going to be, once again, the slope of the integrated form. So back here in the first trial, you graphed time versus concentration, time versus natural log, time versus 1 over, and that helped you figure out, and whichever one of those fit the linear regression best, that helps you figure out what the order is, first, second, or 0. That helps you figure out what M is. You got the slope of that. That helps you figure out what K prime 1 is. You're gonna do the exact same thing again. This time you already know what to graph. You already have figured out the order of the reaction on crystal violet. That's not gonna change. So in other words, in trial 1, if you figured out that 1 over concentration versus time was linear, and that was the best linear regression, it's second order, it'll still be second order down here. So you can jump straight to graphing it, get your new slope, your K prime 2, and you'll know what that value is. And of course, we are replacing K times OH minus to the nth power. We're replacing those things with K prime, which is our false pseudo slope. So we've done 2 trials. We have gotten a K1 prime. We've gotten a K2 prime. So what we can do with these 2 equations now is make a ratio of these and figure out what N has to be. What is the actual order of the reaction with respect to hydroxide? In other words, we're going to be able to do this. K1 prime equaled K times the hydroxide concentration in trial 1 to the nth power. We can divide that by this second equation, K2 prime equals K times the hydroxide concentration in this second trial. This is trial 2, raised to the nth. We don't know what K is. We don't actually have the actual K value. We just have these K primes, but that will divide away. And then we'll be able to now mathematically determine what that N value is. This is why we have to do 2 trials. I think there's like a pre-lab or a post-lab question about this, where you have to explain to me why we had to do 2 trials. We had to do 2 trials to figure out what the order is on the hydroxide concentration. So each time, for each specific reaction that we do, we are forcing the system to behave as if N is 0. We know that N is not really 0, or it's probably not really 0. And so by doing 2 different trials and then making this ratio right here, we can divide out and mathematically actually then figure out what the power, what the exponent of N has to be, okay? Remember that these exponents have to be small whole number integers, like 0, 1, 2, or 3, something like that, first order, second order, etc. Well, because this is experimental in the lab setting, you're going to have some error. You may not get an N that's perfectly equal to 2, for example. You may get an N that's equal to 1.6 or something. You need to round it to the nearest whole number, okay? In fact, I can guarantee you that will happen in this lab. Okay, so this is a lot. I'm throwing a lot at you, but the lab handout goes over this. And in fact, the last page of the lab handout is kind of like a condensed, simplified version of the instructions for this. All right. So you guys are going to look at data. You're going to pretend like we took this data in the classroom, in the lab setting. We mixed some crystal violet and some sodium hydroxide in a beaker, pour that into a cuvette, put the cuvette in a colorimeter, and my laptop will spit concentration versus absorbance data. Because of Beer's law, A equals ABC, I know that absorbance is directly proportional to concentration. So really I have time concentration data of crystal violet. So with that, I'm able to plot a linear regression in 3 different ways, figure out what the order is on crystal violet, which linear regression is the most linear, which one is the best. Okay. And then I am going to be able to get a slope of that, the slope of my linear regression. And getting the slope will allow me then to write it like this. That slope, whatever value I get, is going to be not the true slope, not the true K of my rate law, but the slope of my pseudo rate law, my false rate law that I'm pretending is correct. And I know that because I replace K and OH minus to the nth power, that is what K prime is in trial 1. And then I repeat the whole thing, get data for trial 2, run a linear regression to get the slope of that. I know that K prime 2, which is the slope, is equal to this now. And then I can make a ratio of K prime 1 and K prime 2 to get the N value on hydroxide. All right. And then, so at this point, I know what M is. I know what N is. Now I just need to figure out what K is. And this is really easy because I'm going to have these 2 equations that have K in them. I should know what K prime is. That's the slope from my integrated rate law. I now know what N is. I know what the concentration of hydroxide is. Now I can just figure out what the K value is. So once you've done all of this and you've gotten your N value, first thing you're going to get is your M, the order on crystal violet. Then by comparing your 2 trials and your 2 slopes, you're going to get the N, the order on hydroxide. And now all we need is the K, and I can pick one of these equations, plug and chug and solve for what the real K is. Miss New is asking me a question. She is saying, what do you plug in for the linear regression? Well, Miss New, you're going to have time and concentration data for both of these trials, trial 1 and trial 2. And that's how you, in trial 1, that's where we're trying to figure out what the M is. So you know that you're going to graph time concentration, time versus natural log of concentration, and then time versus 1 over concentration. See which one is the best linear regression. You'll know if it's first, second, or 0 order. That's going to be your M, right? And then the slope of that will be your K prime 1. You do the exact same thing with the new data in trial 2. You already know what to graph because you've already figured out what the order is. You graph it, you find the new slope K prime 2. And those will be these values that you can then plug in and get the N here. All right. I'm going to help you guys with this. I'm going to, I guess, make you do it and try it out. And then after the lab report is actually due, maybe next Monday, we can actually talk about it and make sure that everyone understands how you were supposed to manipulate the data. But from this discussion and from the lab instructions, you should be able to manipulate the data I'm going to give you, hopefully on your own. All right. Now, there is one thing more I need to mention, and this is written in the lab instructions. I want you to think about this. Whenever we go to solve for N here with these 2 equations with my pseudo rate constants, K prime 1 and K prime 2, whenever I go to solve for N, that requires me to plug in the concentration of hydroxide. So this is for trial 1 and this is for trial 2, right? Well, in trial 1, we use 0.2 molar of hydroxide. In trial 2, we use 0.1 molar hydroxide. Well, unfortunately, it's a bit more complicated than that. those are not the true concentrations of hydroxide. As you guys will see in the lab handout, remember what we're doing. We're performing a chemical reaction. We are mixing two chemicals. We are mixing hydroxide and crystal violet, aren't we? Well, these are both aqueous solutions. They're both water-based. So if I take a small amount of 0.2 molar hydroxide, the exact amount is written in the lab handout you need to look at, and I mix it with crystal violet, what have I just done to the hydroxide? I've diluted it, haven't I? I've caused the concentration to decrease because I've just added more water to it effectively by mixing these chemicals together. The actual concentration in my reaction vessel, when I mix these chemicals, the actual concentration of hydroxide is no longer going to be 0.2. It's no longer going to be 0.1. It's going to get cut by some value. So you're going to have to, here in these hydroxide concentrations in trial 1 and trial 2, what I'm telling you is you're not going to be able to use 0.2 and 0.1 because your concentrations of hydroxide are not 0.2 or 0.1. How do you figure out the new concentration of something you've diluted? You use the dilution equation, don't you? Hopefully you guys remember the dilution equation. MIVI equals MFVF. Sometimes I use 1 and 2s, I think. Capital M is molarity, moles per liter. V is volume in liters. So, and VI would be like the initial volume of that chemical. VF is the final volume total after you've diluted it. This is all written in the lab handout. Please make sure you read it carefully. It may help you to go to the last page of the lab handout and look at the simplified instructions. Your concentration of hydroxide is not going to be 0.2 and 0.1. It's going to be less than that because you've diluted it. As soon as you mix it in the lab with the crystal violet, that's adding more water to it. You dilute the hydroxide to some smaller value. So just be careful with that. You're not going to use 0.2 and 0.1 here. Does that make sense? You need to use the dilution equation to calculate what is the actual final concentration of hydroxide, okay? The initial concentration of hydroxide was 0.2 and 0.1, but as soon as you put the chemicals together, you dilute the hydroxide to some new value, some new concentration. So you're gonna have to figure out what that is, okay? All right. Let me look through the lab handout and make sure there's nothing else I need to tell you. So you can read through the methods. You guys need to read through the methods, even though you're not doing it. I'm going to give you the data for it. You do need to understand how the lab was carried out. Just like all labs, you know that you need to create a lab report where you write an intro. In the intro, you have to talk about the purpose of the lab and the theory. Tell me about kinetics. Tell me about Beer's law, etc. And the purpose of the lab is to get the rate law for this reaction. Answer the pre-lab questions. Tell me about the methods. Give me the data. Give me your data analysis. And then use the data analysis to give me your conclusion. Remember that in your conclusion, you have to restate the purpose of the lab. The purpose of this lab is to figure out what the rate law is for this reaction. So you're actually going to give me the actual rate law that you found with a K value and with the exponents N and M. Then answer the post-lab questions. All right. Notice here, the very last page of this lab handout, there are simplified methods, okay? Now, obviously, you're not doing the data collection. You can ignore that. You can jump pretty much straight to step 6 because you're gonna have absorbance versus time data. You're not going to have to collect it yourself, obviously. I'm gonna give that to you. All right. And then there's simplified steps here to get the order on hydroxide and then to get the rate constant, okay? All right, so I know that was a lot, and I know that it's a bit complicated to think through this part, but once you guys get your hands on the data and start doing your analysis, hopefully it will make more sense. And again, I'm sorry that we don't get to do this lab in the lab. Obviously that's out of my hands. if you all have questions while you're doing this, I need you to get in touch with me, email me, whatever you need to do to ask me questions. I'm going to leave this lab up to you. It's going to be due Sunday night. We'll go over it together on Monday or sometime next week, hopefully. If you guys are just really struggling, you can let me know and we can look at it maybe a little bit before that. Please make sure you know what to do for the rest of the week. There is Kinetics video 3 posted. You have to watch that, take notes over it, and then be working on the packet. On Wednesday, we'll meet again through a Zoom meeting to talk about questions in the packet, go over some of those homework questions. Thursday, we'll do the same thing and we'll review for the exam. The exam over kinetics will be on Friday. So right now you have three things really you need to be thinking about: the lab and the lab report, watching that new kinetics video and taking notes over it, submitting those notes as an assignment tomorrow. And then the third thing is working on the packet. All right. Are there any questions that anyone has for me? Again, I've recorded this, so if you need to go back and watch it, I'll post it on the YouTubes. You guys feeling okay? Everyone's good? Okay. I got a few thumbs up. All right, well, you guys know that if you need anything at all from me, please reach out. It'll be your responsibility to reach out. And I'm here for you. I'm here to help you guys be successful. I know that this is all kind of a weird, wacky situation that we're in, and it's new to everybody. It's new to me, but I'm here for you guys, and I want you all to be as successful as you possibly can be in this class, on the AP exam, in life in general. So please reach out. Let me know what you all need. So if no one has any questions, I'll let you guys go. Please make sure you're working on those 3 things I gave you to do. One thing real quick. On the Google Classroom, I have put the lab, I've put the lab as an assignment. So remember that you have to give me your full typed lab report due on Sunday night. And in the lab assignment is where you can access the data for the lab, okay? Let me just show you what it looks like. I should have thought about this earlier. Here's what the data for the lab looks like. There's data for experiment 1, trial 1, and I give you all the information there, time and absorbance data. And then there's data for experiment 2, where we use now the 0.1 molar sodium hydroxide, time and absorbance data there. So that's the data for the lab. You can download that. In the lab assignment on the Google Classroom, okay? The lab handout itself with the instructions are, you can access that like you access all the labs in the My Haiku class website, or I've posted it a little bit farther down in the Google Classroom, all right? Okay, so be working on the lab, watch the video, take notes over the video, upload those notes and turn them into me, and then be working on the packet. All right, we will meet back on Wednesday at 9:30 on Zoom to talk about questions in the packet and see what questions you guys have about the third kinetics video. All right. Okay. Thank you guys so much for your time. Hang in there. If you need anything, let me know. Otherwise, I will talk to you all later. Thank you.